All right, team, here we are, the final lecture. Just want to say that you guys have been great through all this. It can't be easy having to do all this online. You guys have been wonderful. We figured out a lot of stuff throughout the term. Hopefully you've seen that I've been trying really hard to take into account all of these technical challenges. You've probably seen that I've posted information about the exam. Make sure you check out that email. It gives you some really good information on what the exam is going to look like and how we're going to follow it. I am, after I create the exam, going to go through it again and again and again. The TAs, all 4 TAs, are going to go through it looking for typos, and I'm going to get a couple other engineering friends to go through and complete the exam. So if we can all do it, hopefully we have no issues with weird typos and data sheets. You've probably all seen that upload that the Steelbook changed the section properties for a few different elements. So I'm going to be following everything that I previously posted for you for the exam, and next year will be a new year. But there's very, very little difference between those things. So much so that they didn't even make an announcement about it when they changed it. So in real practice, those differences would have been meaningless and worked out to a kilonewton or two difference. So not something that would have made a design issue problem. And so for us to be thorough, I'm going to follow everything that I uploaded for you guys, which is just a 2-year-old version of the Steel Code. Not even the code, the handbook that goes with it. So don't worry about that there's something I've taught you that's wrong. It's just a small editing update. So today's last lecture, it's going to be pretty easy, pretty low-key. We're going to talk about foundations. There's going to be 2 small calculations we're going to go through in this lecture, but they're so small that I'm not even going to branch off and do kind of the calculation mode of my camera. But there are a few great exam questions throughout this lecture. You'll probably be able to identify what ones those are. You'll probably see something similar in the quiz and assignment as well. So we're going to talk about foundations, and we're going to talk about lateral load resisting systems. They're both incredibly important parts of the structural engineer's components, but they tend to get glossed over in the architectural world between engineering and architecture. So this is the place that we're going to talk about those things. Oh, I've moved my keyboards off to the side there. Okay, so the role of the foundation. What we want to do is make sure our building doesn't sink down into the center of the earth, and the thing that's stopping our building is the soil. We want to make sure our building doesn't slide along the ground, and the thing that's doing that is the soil. It's the friction where the building interacts with the soil. And the other thing we want to do is make sure our building doesn't tip over. And so on one side, it's the soil stopping it, and on the other side, either the weight of the building has to hold down the back corner, or we have to hold it down with something, and that would then involve the foundations. So the job of the foundation is to not fail, not experience unreasonable amounts of settlement, and so there's 2 things we worry about there. The building deflecting or moving down as a whole, or differential settlement. So you can imagine if you've ever walked along the beach, for example, on a day where there's big surf, you could walk on the dry sand or the hard packed sand or the wet sand, and if you plopped a building there, you could imagine that it would react to the loads differently in each spot, and that happens in real life with a building. So there are 2 criteria we design to: the total settlement and differential settlement. And then the third thing that we worry about is heave, and that is about frost. When water freezes, it's a unique material in that it expands when it freezes. And when it expands, if it's underneath our building when it expands, it can lift our building up. Seems far-fetched to imagine that, But if you've ever seen fence posts that are popped up out of the ground, what's happening there is frost heave. So what we do is we make sure our foundations are down far enough that ice or water, when it freezes, can't be underneath the foundations. It doesn't mean that there's not water there, but the cold air above can only penetrate so down so far into the ground. And in southern Ontario, that's 4 feet. So the majority of our region is 4 feet. Now, normally, all of you are here in southern Ontario when we're talking about this. I know you guys are scattered across the globe right now, but we're talking about most of this as if we were in southern Ontario. Different regions have different frost depths. Florida has no frost depth, for example. The reason we have basements most of the time is if we've got to go down 4 feet anyway, we might as well go down deep enough and give ourselves a basement. In places where the frost is incredibly deep, I think in Edmonton it's 9 feet, something like that. There, they might not do a basement because they do a different type of foundation system. In Florida, you rarely see a basement because you can just keep your structure pretty shallow within the soil grade. So locale makes a big difference for that. But frost heave is a big consideration, especially in Canada. And in southern Ontario, 4 feet is the number we worry about. So what's settlement? How can our buildings settle? Intuitively, you know it when you step on the ground. Depending on what type of ground it is, you sink down. What's really happening is the particles can realign. If there's any bakers, if you've ever taken a thing of flour and bang it, it realigns and all of a sudden it drops down in its height. We could lose moisture that's in the sand, and so the volume decreases. We could have a mix of big particles and small particles, and if water or something flows through, the small particles could get washed away, and then the big particles clump together more or settle relative to each other. For those of you that do live in southern Ontario, you know water main breaks and sinkholes can plague us in the wintertime. The frost breaks the water main bursts and water runs below grade and we don't know about it, and it washes away all the fine particles, and then we end up with a base sinkhole. What can we do about differential settlement? You can see here that this side is on less stiff soil, and so it's sinking more and we end up with cracks. It's not great to have the whole building settle, but it's worse to have part of it settle because that can actually damage your building. We can maintain low bearing stresses. We can proportion the footings so that it evens out the load to be the equivalent stiffness, similar to what we talked about with concrete and load sharing. We can bear footings on the same soil type, so we can ensure that we do have the same consistency of soil below both of these things. This footing here, good soil might be down a little bit further, so we might have to dig this foundation to be a little bit deeper than this one, just to make sure we're on similar types of soil. So you're probably asking yourself, how does soil fail? Where can it go? Why would we worry about that? What does that look like? Well, when soil fails, it fails on a shear plane. So if the foundation is causing an overburden or trying to fail the soil, what really happens is the soil underneath it shifts out and you'll get a whole big blob of movement off to the side. So you can see here, this would be the shearing plane of the soil failing due to this load on our footing. Where we get our information for our soil capacity is from a geotechnical investigation. A different engineer is hired specifically to do the geotechnical investigation, a geotechnical engineer or a soils engineer. They cannot be hired by the architect or the structural engineer. and strongly discouraged from being hired by the contractor. The owner is responsible for hiring the geotechnical engineer. It limits liability from the rest of the team and that they're working directly with the owner. But owners often don't have construction experience. They don't know what to ask their geotechnical engineer. So what we will do as the design team is guide the owner in what they need from the geotechnical engineer. So we will create a terms of reference where we give that to the owner to issue to geotechnical engineers that we recommend. And we'll say, okay, you need to dig this many holes to look at the soil. You need to bore down and extract soil and test the soil with different parts. And we're looking for things like seismic capability, bearing capacity, differential sediment capacity, and the level of good soil. Where is the good soil? And that's what we ask the geotechnical engineer to give us as the designers. The geotechnical engineers, once one of them is hired, they give us the bearing capacity for strength. They give us a bearing capacity for settlement. So remember, those are a different set of load combinations. They give us earthquake criteria or seismic criteria, and they give us the depth required for both bearing and for frost. So as much as we may only need to go down 4 feet for frost, good soil might be 10 feet down and we have to excavate down to there. Sometimes it can be even further and they might recommend something else that we do. I have a project right now where we're going down 3 meters for a basement and good soil still isn't down there. So they have to remove even more soil from the site and build it back up with good soil, or what we call engineered fill. And then they often give recommendations for foundation construction. Most of the time in southern Ontario, those are spread footings. Whether it's a pad footing below a column or a strip footing below a wall, that is most often the common type. In Edmonton, for example, caissons are the common type of foundation construction. We might see caissons where we have bad soil. In Edmonton, they do it to go down for frost, for example. And I'm going to talk about those things more when we look at pictures of different types of soil. As much as they give us the bearing capacity of the soil, base building engineers often don't have that report when we start the design. So we have to make some early guesses to at least be able to start for schematic design and preliminary costing, so the owner even knows if they want to build this thing. We often recommend getting the soils report as early as possible. There's not often that we say, no, you can't do something, but a soils report can say, no, you can't do something. Or it can add a huge expense to a project. I had a project that was going out last year in a rush. Actually, I had 2 projects going out in a massive rush. And both of them I said, the biggest risk here is that we don't have a soils report yet. We should focus on getting that ASAP. Everyone was so busy and the owners weren't as experienced as maybe we would have hoped. And the soils report didn't come to us until late in the project. Both projects, there was normally you kind of have a good idea of what's happening on the site. You might reach out to people who have done other projects nearby and take a glimpse at their soils report. You still need the final one for your site, but at least gives you a heads up if there's anything surprising. Both of them, projects nearby, had no big surprises. Both of these projects, massive surprises on the soil capability on the site. One of them, we have to go down super far for fill. We cannot build on the soil that's there. We have to remove all the bad soil, build it up with good soil, and then build our foundations. The kids are fighting politely. I need this, please, Malcolm. No, thank you, Duncan. I'm playing with it. It's a touchy game because it can turn sideways in a second to the teething 2-year-old bashing the other one in the head with the train tracks. Sorry, but because of that, we often start with some preliminary things. If we have nothing, I will often say, hey, it's safest to start with the fact that we've only got 75 kPa. We can confirm it all later, and it's always good news to find out you can reduce your footing size. But it really sucks to find out you haven't allowed for a big enough footing. So if I don't have any information, I'll start with 75 kPa. If I have some information about a nearby project, I might go with 100 or possibly even 150. If I know we're going down to sound rock for something, which is rare, you can get really high capacities. Most of this would then be given information from the geotechnical report about what these capacities are. So to achieve that bearing capacity, the soil must be undisturbed, no organic materials, and it must be cleaned by hand. That doesn't mean get down with a little brush. What it means is no rocks and not just a backhoe digging it up, but that it's relatively smooth and flat, maybe tamped down, so that we're on something flat, giving us a nice, sound, solid foundation base. The big one here is no organic materials, and soil must not be disturbed. So for projects kind of down around Leslie Spit, I'm doing Tommy Thompson Park, the new pavilion building. It's at the entrance to the park. For those who aren't from Toronto might not know that everything south of Front Street is fake. That's all built up with soil from construction from around the city. So all of that material, not only is it disturbed and have organics, it's actually man-made terrain. So there we need very, very specialized foundations, and I'll show you what those kind look like. But most of the time, they're doing spread or strip footings. So, spread footings. If it's below a wall, we have a long strip of footing. So you can imagine that we have the wall of the building coming down here. Maybe it's a concrete wall, maybe it's a masonry wall, maybe we have a series of closely spaced columns. And then we do a pad footing underneath a singular column. These often have higher point loads coming down on them. Sometimes you might see a strip footing with a notch out for a pad footing because we have a column kind of almost along the wall, or the strip footing below the wall isn't enough and we need to bulk it out for our pad footing. If you go back and look at that very basic preliminary project that I showed you guys as an example in the first or second lecture, you'll see that we had strip and pad footings, spread footings below that project. So, as with everything, we need our reduced capacity to be greater than our factored load, or our capacity greater than our load for serviceability conditions. Duncan, thumb down! He's standing up on the train table. Yes, buddy? No, I'm teaching a class. Oh. Malcolm says hello to everybody. Our reduced capacity has to be greater than our factored load. If we're talking about strength and if we're talking about serviceability, the capacity they give us has to be greater than the load. Remember, there are different load combinations. The F means that it's an ultimate limit state versus a serviceability state. They give us this value with the R, or the reduction capacity or the reduction factor already embedded in the value. If you guys remember, stress is force divided by area. If we're talking about the load that we have coming down, we want to know what the area of our footing is, and we can calculate what our BF is. Well, if what we want to know what this area is, we know that we can go up to just as high as BR. If BR has to be greater than BF, we can substitute this out here, and if we know BR, because we've gotten it from the soils report, and we know what BF is, because we've figured that out from everything we learned earlier in this term, we should be able to figure out what area of footing we need. Rather than check an area, see if BF is less than BR. Check a different area, see if BF is less than BR. We could just figure out what the perfect area is to get those two things as close as possible, because that's the most efficient, but still make sure this is just a tiny bit less than this. So let's take a look at an example of that. This is as hard as these calculations are going to get. We have a column with a total load of 1,000 kilonewtons, and it sits on a spread footing bearing on till. Assume that a square footing of dimensions d by d will be used. What is the minimum dimension that can be used? Now, I'm going to specify here that we don't like to do things not in 50 millimeter increments. So the same thing we did with our wall dimensions, we're going to do, and our beam dimensions, we're going to do with our footing dimensions. Now, that seems not fair in an exam, for an example. So for an exam, it might just be nice enough to make sure that the calculation worked out to be exactly around a nice round number in 50 millimeter increments, rather than make you guess what dimension I would want. I would probably build that right in, or I would specify round up to the next nearest 50 millimeter increment, just so that we're all on the same page. So what is the minimum dimension of D that we can use? So we know that we have a footing that is going to be square, so D times D is area. We know that BF equals PF divided by A. We have a load here of 1,000 kilonewtons. But if we substitute BR in for BF, we should be able to find out exactly what area we need. The only thing we don't know now is BR. Normally we'd go to our soils report, but it's a bit early in the project. So let's take a look what bearing capacity till has. So let's go back a few slides. Till, ooh, lovely, 200 kPa. That's a nice high number. So we've got some good soil there on our project. So we look up the bearing capacity on the table for till. We see that BR equals 200 kPa. BR is going to be our P divided by A, or kilonewtons divided by meters squared. We have 1,000 kilonewtons. BR equals P divided by A. Why don't I just rewrite that so that I know what A is? So bring our A over, divide by BR. Area equals P divided by BR. Well, I know I've got 1,000 here and 200 for BR. Well, 1,000 divided by 200 is 5. We've got 5 meters squared. So our footing needs to be 5 meters squared. Well, we know that that could be kind of a varying sequence of dimensions, but it could be a rectangle, but they've told us explicitly that they want a square footing, not a rectangular footing. If it was a rectangle, they'd have to tell us what side one of the sides was. Maybe there's some criteria on the site that we can only have one particular dimension. But they've said, no, this is a square footing. Tell us what size this footing needs to be. Well, the dimension is going to be area squared, because area equals D times D. So D equals the square root of A. We get 2.236 meters. So we want a square that is 2.236 meters by 2.236 meters. That's a ridiculous size to tell a contractor to form. This is where I would make sure on the exam I gave you a nice round number here and made that on a nice even 50 millimeter increment. But for something like this, if I was drawing this on my drawings or specifying something on my drawings, I wouldn't do 2.236. I would do 2.25 by 2.25. I'd round that up to a 50 millimeter increment. And so this would be the footing I would specify on my drawings. So what if we had a wall footing or a strip footing? So we have a wall, maybe it's a brick wall, a block wall, or a concrete wall, picking up some floor load, we don't know. They've just told us that 20 kilonewtons per meter sits on a strip footing with a width B and it's bearing on loose sand. Well, we know that we can look up what B is, or BR is for loose sand, because again, we don't have a geotechnical report, but we could go look that up. What is the minimum dimension for B? Well, we know that B equals P divided by A. P, they've given us 20 kilonewtons per meter. So if this was 1 meter of wall, we've got 20 kilonewtons. Area, we know it's B times some dimension. Well, what if we also picked 1 meter? That would be kind of easy. We know it's a continuous wall, but let's look at 1 meter increment of it. So we've got 20 kilonewtons on B times 1 meter of wall. We want to look up the capacity for loose sand. Boop, 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 boop. Loose sand or gravel, 50 kPa, so it's really crappy soil. So we look up 50 kPa. We know BR equals P divided by A. And we know that this is 20 kilonewtons per meter, or 20 kilonewtons every 1 meter by B. So P equals 20 kilonewtons by our 1 meter, and L is the length of the wall in meters. And our area is going to be B times L, which is, we're going to use 1 meter. So 50 kPa equals 20 times L, or 1 meter, times B divided by B times L, but we're going to use 1 meter. So you could say L cancels out, or 1 and 1. We can rearrange this. So 50 equals 20 divided by B, or rearranged for B, is 20 divided by 50, or 0.4 meters. So our strip footing needs to be 400 millimeters wide. And it needs to be at least 400 millimeters wide. If it was 350 millimeters wide, well, let's just take a look at that. If we had 0.35 times 1 meter, it's 0.35 meters squared, and we have 20 kilonewtons divided by 0.35, we would have a BF of 57 kPa. That is not less than 50 kPa. So we need something bigger than 400. 400 works. 400 or bigger is going to work for us. So how thick is a spread footing? If you don't want to design this, a good rule of thumb is make this projection as big as this projection. So if this was a 200 millimeter thick wall on our 400 millimeter thick spread footing, so that's 400 wide, our 400 millimeter wide spread footing that we just calculated in our strip footing calculation. And if that's a 200 wall, that means this is 100 and this is 100. Oddly enough, we wouldn't go less than 200. I'm going to add that to this, not less than 200 millimeters. We often would keep that at least 200 millimeters thick. Just, it's easier to get the rebar in. It's 4 inches is not easy to work with. We want something that's at least around 8 inches thick. Stepped footing. I showed you guys this earlier in the term. If we have to drop our footing down because maybe we have a zone with no basement and we drop down to a basement, or maybe we have a sump pit or an elevator, we can't just do a straight drop. This load starts to damage this load. We have to step down our footing. I uploaded at the beginning of the term typical details for you guys, and you can go take a look at those and see this detail worked out in great detail for the strip, for the stepped footing. Another type of foundation is caisson or drilled piles. So these are where we remove soil and put concrete in its place. We'll often use an auger and pull the soil up as we drop down a sheath or a lining, and then we'll fill that hole with concrete and rebar. We get bearing on the end of the caisson, but we also get friction along the side of the caisson. So we form the caisson, and as we load it up, it's not just the bottom that's resisting load, but the fact that it's trying to slide down against the soil here as well. We often use these where the soil up here isn't very good. So all of those sites on fill that I talked about, like the Tommy Thompson Park Pavilion that I'm doing, where all of the site is basically crappy soil, we're doing caissons is one of the big options there. That particular project, we're doing a mat footing, a very large spread footing, but a nearby project that I did used a wide variety of caissons on the site. They're really good for heavy loads too, and actually in Edmonton, where they have to go down for frost, they use caissons or drilled piles as well, just to get down to a depth where they don't have to worry about frost heave underneath this. And what they'll do is they'll build something similar to foundation walls down far enough that they span from caisson to caisson. Belled caissons are where we actually make the bearing capacity at the bottom work for us by making the bottom bigger. I had always heard of these, but in Toronto, the machines that make these bells aren't very common. So you can imagine that either you have to make your hole big enough to get that soil out, or you need a machine that goes down with a hole this size and then flares open and scoops out extra soil. And in Toronto, that's not a common machine. In Edmonton, like I said, where they do so many caissons as their standard foundation type, all of the machines have the belling capability. So I did a project in 2009, 2010, and we specified belled caissons on that site. Piles. Piles are where we actually drive something into the soil. We'll start with a length of it, and we'll drop a heavy weight on it and hammer it like a nail into the soil. Often, since we're worried about that thing buckling before it's in the soil, once it's in the soil, it's not going to buckle because it's being braced by the soil. But while it's up out of the soil, we have a heavy weight hammering on it, and we don't want it to buckle. You can imagine trying to hammer in a spaghetti noodle. It would want to buckle. But a nail, which is a little bit wider, resists that a lot better. So if the soil near the surface isn't very good, we might use piles, or even a cluster of piles, and I'll show you that in a second. We often will use stubby or very square-looking profiles to help limit buckling. And if they have to drive these quite deep, they might hammer in a section and then weld on another piece and keep hammering it. So a pile group, we would do a series of piles and excavate down to here, keep driving the piles, and then cast them all into one object, so one point load spreads the load out onto a series of piles. Engineered fill is what we might do if we have really crappy soil over the whole site. Often we'll just dig down locally where we need to get our foundations down. But something like a rink, for example, needs pretty high capacity everywhere below that rink. And so in a site like that, we need engineered fill. So literally, they scrape the whole site clean, remove all the soil, and put down engineered fill. And that will end up with 150 kPa. I have a very large project right now that has engineered fill going in on site. Actually, two projects right now going in with engineered fill on site. So they get down to a level that the soil is good and then build back up with engineered fill. Or basically fill from another site, but they've calculated its capacity. And then they compact this soil to 24 kPa. And you'll see why 24 kPa is important in a few minutes. If we don't have to worry about that everywhere, but we don't have good soil, what we might do is excavate locally or trench the footing and put engineered fill locally for our stripped footing. For our strip footing. I said I had two projects with engineered fill. One of them is doing this trench footing method locally for the high loads under the walls. A helical pier is another good thing to do in crappy soil. These literally look like big screws that get screwed into the soil, and as they screw down, they start to resist load. If you've ever manually tried to screw in an IKEA screw with an Allen wrench, you know that it starts to get really hard to turn it because there's more of it resisting load. That's the exact principle with these helical piers. These are proprietary products that are engineered by the supplier. So they are responsible for the final design. What often happens in these projects is the base building engineer is given a preliminary feedback. The helical pier suppliers will look at the geotechnical report and give feedback on capacities. The risk is that when they actually screw the piers in, they might have a different capacity than what we estimated. It is a risk to the owner. It is often that they come out better than we expected, but sometimes it's worse. And in that case, the owner needs to be able to pay to get the capacity that we need. So one nice thing is they can go in a rush. You don't have mass excavation, but there is some risk involved to the client. One nice thing is that if it is a big rush project, it delays some of the design component to the construction phase. So you can buy yourself some time that the base building engineer might have been focused on complex foundation designs. A mat foundation. So this is what I said I did for the Tommy Thompson Park Pavilion. Again, we had really crappy soil. So instead of having high point loads locally, we spread the load out on a really deep, thick foundation everywhere on the surface. So we make this nice and thick, so a point load here spreads out while it goes through the thickness of the footing, so it spreads out on a bigger area on the bottom of the footing. For anyone who's ever been to a cottage with a dock, you know that timber cribs are often the way we support structures in the water. So these are literally, you build a square with some wood, you put a mesh in, or you put some wood planks down, you drop it, you keep adding wood to it, and you fill it with rocks. So it sinks down, it sits on the bottom, it's weighted down with the rocks because the wood would want to float up, and then you start to build your construction on top of it. Slab on grade. Slab on grade is the floor that just sits on soil. So it's not our strip footings, it's not our spread footings, it is the very bottom level of floor that we have on a project. So if you have a basement, it's the floor in the basement. If you don't have a basement, it's the thing sitting on the soil. It's typically used for interior applications because if it is susceptible to frost, so we'd have to do something to limit its interaction with frost outside. We often cast it on a layer of clear crushed stone, which is on often native soil, if the native soil is pretty good, but it only needs 24 kPa of capacity. That is ubiquitous, that is standard for a slab on grade to have a BR of 24 kPa. So most soil, you saw from that chart that most of the soil types, assuming it's undisturbed and it doesn't have organics in it, 24 kPa is okay. So why do we worry about frost? So here you can see where we can have the soil leave the zone and we end up with a void, or it can freeze and lift up the soil. So what are alternatives to going down 4 feet? Sometimes on sites that's a really hard thing to do. What we really are worried about is protecting our foundation, but also our slab. If we don't have big footings nearby, so this would, for example, be my mat slab that I have on the Tommy Thompson Park. It is an outdoor, it's not an insulated building, or all of it is not insulated. So we're worried about frost here getting down into our soil, but we're also worried about frost here getting down into our soil. So we actually need to build our slab on grade on insulation. So here's our soil capable of 24 kPa. Here's our clear crushed stone. And instead of the clear crushed stone being on the native fill with the 24 kPa capacity, we've put this layer of insulation in between it. And we've protected over here to make sure the frost can't get at it. And here's the next slide that talks about that. Assuming this is a heated building, what we want is the sum of these distances to be 4 feet. Often we want to go down at least 2 feet so that if somebody was planting a garden here, for example, we don't dig out underneath our footing or hit our insulation. But we could go down 2 feet and over 2 feet because this might freeze, but it's protected by the insulation. Our frost would have to come down and over 4 feet to freeze this soil right here. And it's that summation of frost traveling 4 feet that is the real kind of kicker. If we have a slab outside, so this is a slab on grade outside, here's our building, we could do this on an insulated slab and extend our insulation out 4 feet. That's an option. Or what we'll often do is a frost slab. A frost slab gives us an air gap in between here. So this soil might freeze due to the frost coming down through the concrete. But if it heaves, we don't care because it's not going to hit, it's not going to take that slab up with it. So where do we do frost slabs? They're often very important at major means of egresses in a building. The idea is that for barrier-free access, we need this to not have a lip at the door. Back in the day, what they did was just drop this down, and who cared if it heaved? We just had a step here. Because you can imagine, if this is the way out of the building, the door needs to open, and if this heaved, your door is going to bash against the concrete that's heaved. So we used to build them just down a step, no big deal. Obviously, that isn't great for accessibility, and so people in wheelchairs, mobility issues, even moms with strollers. It becomes really hard to get into this building then. So we now build these slabs flush, so we need to make sure that there's an airspace in here. What they often use is a void form here. So basically it's cardboard, really stiff cardboard, that fills that gap. They cast the concrete on it, and then moisture gets down and the concrete deteriorates. Or if the soil does heave, it'll actually crush the concrete, not lift the entire. It'll crush the cardboard and not lift the concrete. Retaining structures, anything that holds back soil. Normally, and I showed you kind of what these soil pressures look like, the wall is braced at the slab at the bottom and a floor at the top. So think of it as a beam kind of spanning from here to here with a varying load on it, or a triangular distribution of a linear load. If we don't have something bracing the top, this thing wants to tip over. We can resist that a few ways. A dry stone wall, Well, we need our bottom to be big enough so that if it tries to tip over, it can't. It's the equivalent to when somebody pushes you over, widening your stance just a little bit. Or we can do it concrete. So you can see that we have a footing here that's resisting soil as it tries to tip over. One of the nice things about this is the weight of the soil is actually helping resist it from tipping over as well. This is nothing I'm going to test you on, but someday you're going to need to draw on a set of drawings very quickly a retaining wall, and you're going to have no idea what it looks like, and you're going to draw it, and it's going to go out on a drawing set, and then the engineer might need to engineer it, and you might be surprised what it looked like. So when you have to do that, come back and look at this slide. These are typical proportions of a retaining wall. So if you know that this is 4 feet for frost, and you know how much you have to retain here, here are some good dimensions that you can draw on this. So about 10 inches at the top gives us lots of room to fit in rebar, and then some proportions on what that footing might look like. Why would you build this one or this one instead of this one? Well, if your property line is right here, or if your property line is right here, would decide why you might do one of these footings. Maybe your property line's over here, and then this is going to be the most efficient system right here. Timber retaining walls. The difficulty here is that we have to have a dead man, or essentially it's something that drives back into the soil or is built before we fill in the soil to gather the weight of the soil. So as this tries to tip over, it's trying to lift, it's trying to take that with it, and it's engaging the weight of all of this soil as it tries to tip over. Modular block retaining walls. These are usually designed by the proprietor or the company that sells these walls. But again, often you might get your base building engineer or yourself to draw a quick version of it on the drawing. So nobody has a big surprise when it comes time to actually price this project. So you've all seen these modular walls kind of on the sides of highways, landscape projects. They're pretty common. Gabion walls, I find these pretty awesome, where they take mesh baskets and fill them with rocks. I'm actually working on a project right now, well, the Tommy Thompson Park Pavilion with DTAH. They're doing kind of a beautiful architectural version of this that's going to look absolutely stunning when it comes out. Shoring. So shoring is what we do when we need to retain soil, but it's not the final structure. Where you might see that is when you need to retain soil that's not braced at the top by a floor temporarily. So if you're in a major city and you've been walking down the street, you know that you've stood on the sidewalk and been able to look into an 8-meter deep hole right beside you. The way they do that excavation is they dig down 4 feet, and they drive a series of piles, so that would be our steel elements, and then they dig out 4 feet of soil, and they drop pieces of wood in between those pieces of steel. So if we were looking at it from the top, and this is a really bad drawing, I apologize. You look rough, man. Thank God it's December 1st, and it's Upper Lip Liberation Day, and that mustache is going. And he's got clear glasses on, so with the gray hair, the gray mustache, pale blue eyes, and white shirt, gray shirt, and clear glasses, he looks like a ghost walking around my house. It's disturbing. Okay, so imagine that they drive these steel members into the ground, and then they excavate 4 feet over here, which you're allowed to excavate with no restraint, and then they drop these pieces of wood in. And then they dig down 4 more feet, and all of those pieces of wood drop down with it, and so you're left with 4 feet at the top, and you drop more wood in. And then you dig down 4 more feet and drop more wood in. And so you do that again and again until you get the excavation you want. Really important on sites where we often have, there's a slide I'm gonna add for you guys that shows excavation lines, because we often excavate at a 7 to 10 slope. So I don't think I've added it here. No. So I have drawn it in another series of slides. I'm going to bring it in and drop it in here. But I'm going to show you right now on the screen, so you guys will have this slide added in. We need to excavate. We can have 4 feet straight excavation with no worries in most soil types. But we can't do more than 4 feet deep with no kind of restraint. So what we'll often do is excavate at a 7 to 10 slope. So to give you a sense of that, if this up here is grade, and this is where our building is going, we can excavate 4 feet, no problem, but then we need to slope back at a 7 to 10 slope. If our property line for those big buildings we do is right here, and we need to excavate down 8 meters, let's just take a look at that. 8 minus 1.2 leaves a 6.8. That means we'd need to excavate away from the site almost 10 meters, which, you know, in major cities, you're pretty tight to the property line. So that's where you might need shoring to be able to do your construction. So let's move on to the second part of our lecture, which is lateral load resisting systems. This is what keeps your building from tipping over. So we need lateral load resisting systems on every floor, in every direction of every building. I can guarantee you that this is a question on the exam. I have done this question where this is the only answer, and people haven't believed me and haven't answered it. I have done this where I say, the answer is A, and it's this. And then I give 3 other options that say, this isn't the answer, this isn't the answer, this isn't the answer. And people get the question wrong. And it boggles my mind. Every floor, every direction, every building, all 3 of those together are a truth. I had a student one year and I asked them in their comprehensive studio class where their lateral load resisting system was. And they said, oh, it's only a 1-story building, I don't need one. Well, if you've ever seen barns that are tipped over, the ones that have the big doors, that the doors have been removed, tipped over. You need a lateral load resisting system, even for a 1-story building. So, the role of the lateral load resisting system is to carry loads due to wind and earthquake from the floor diaphragms. So that's the floor surface we walk on, and that's what stops it from racking out of plane. And it transfers it to the walls that keeps it from tipping over. That diaphragm is what keeps the building square in plan. So we have to be able to get the loads to those lateral load resisting systems as well. And that's our floor diaphragm. Well, we need it not to fail under load. We need it to prevent the building from deflecting excessively. And we need to stop the building from tipping over. So what different types of lateral load resisting systems are there? We're not going to spend a lot of time on this because we've talked about it a bunch. And then I'm going to show you a series of pictures that you've already seen because we talked about them in the different material types. But if you have a wall, you might as well use it as your lateral load resisting system for things like concrete, masonry, and wood shear walls. You might as well use them if you got them. You know that expression, smoke them if you got them? Well, don't smoke, but use your walls if you've got them as your lateral load resisting system. If you're talking about a steel building, often your walls are just cladding. So for those buildings, X-bracing or diagonal bracing is going to be your best bet. You can do an A-framed or a 3-pinned arch, and that is And we talked about this a little bit when we looked at steel, but I'm going to bring it up again right here, where we have a pin, and a pin, but these two things prop up against each other. So literally an A-frame. If these are propped up against each other, for this one to tip over, this one resists it. For this one to tip over, this one resists it. And then we have moment frames, or sometimes called a portal frame. And that is where we moment connect corners together. Moment connections are expensive and difficult to build, and they make things bigger, and they're less stiff. So we don't like moment frames unless we have no other choice. If you have no other choice, a moment frame is a wonderful solution. But don't start at moment frame. It's going to be super expensive, and you're going to have much bigger members if you're trying to fit in a tight space. So what do you think about when you're trying to pick your different system? Well, think about what the industry standard is for that building type. If you're doing a hockey arena, braced frames in one direction, and an A-frame or a 3-pinned arch in the other direction is ubiquitous. Industrial buildings, braced frames. A concrete building, well, concrete shear wall. There are pretty good standards for each building type out there in the industry. Start there. If you have a problem, then start thinking beyond that. But if what you're already doing is the norm, you might as well go with it. You need to think about flexibility. How much does it move? What are the applied loads? Is it seismic or wind? Because seismic can have some very strict stipulations on what you can do. We're not going to go into that now, but I just want you to be aware that if you're in a high seismic zone, the engineering of those lateral load resisting systems can be much more onerous. There's a lot more work involved in it, like quadruple the engineering involved in that. And then you need to think about your floor and roof system. If you have a particular floor and roof system already involved, you might as well use the braced frame system that works with it. If you have a steel building, well, you might as well use steel braces as your system. Unless you're using a steel building that has an elevator core, well, the standard there is your elevator core is concrete. You might as well use it because you've already got it for fire protection of your major means of egress. So for wood construction, perimeter wood stud walls as a shear wall. That would be your standard lateral load resisting system. Again, this is common. It doesn't mean it's the only option, but if I ask you a question, say on an exam, which one is most common for this? Well, come take a look at this list. The answer will be right here, I promise. Hotels and condos, it's probably going to be a concrete building, so it's probably going to have a concrete shear wall. Even if it wasn't, it probably has a concrete core, or stairwells, or elevator cores, so you might as well use the concrete shear wall. Schools often use load-bearing masonry shear walls. Commercial buildings might use a concrete shear wall and tilt-up. Industrial buildings and warehouses, braced frames. Almost always a braced frame. High-rise office buildings, they might use concrete shear walls or cores, or they might do a steel bracing or a combination of those. So those ones, it really can be project specific. Arenas, moment frames or A-frames in the short direction and braced frames in the long direction. I'm just gonna add that, just for arenas in long direction, because often that's what they'll do. So what can't we do for lateral load resisting systems due to seismic? Like I said, there are very onerous requirements for seismic. In Toronto, we don't have that high of a seismic zone. So we're not allowed to have a weak story. So if we have a a really tall building, for example, and we had brace frames coming all the way down our building, but then we wanted a big open area on this floor. It doesn't matter if this is strong enough to resist the loads. What we can't ever have is a story below another story with only 90% or less of the capacity. So we can't, if we have for other reasons a lateral load resisting system that's stronger above, we have to make sure we have something with enough capacity below. So gold ring, for example, we had trusses that were very, very strong for lateral loads. And the code has been clarifying that communication somewhat, but it became a lateral load resisting system, even though it wasn't what its intent was. So we had to go through great engineering to talk about what was happening for the lateral load resisting system on the floors below. We can't have too much torsion. So torsion is what I was saying in plan. So say we have a nice building with an elevator core right here. So it's strong enough in this direction and this direction, but if our earthquake kind of comes at a corner, our building might try to twist. Might be strong enough, but our center of rigidity of our building isn't at the center. So it's in the center in one direction, but not in this direction. So even in this direction, our building would have a tendency to twist. So for something like that, we might need to add some braced frames out there, even though we didn't need it for strength, because that wall was strong enough, we might need it for torsion. In high seismic zones, there are other criteria that we don't have in low seismic zones. You can't shift the lateral load resisting system. So if your lateral load resisting system is coming down in one plane, you can't jump around with it. We can do that in Toronto as long as it's not weaker than it. We can shift it. We have to connect them, but you can shift it. In high seismic zones, there are very specific capacity design requirements. Capacity design means that we actually allow the building to move. And once we allow the building to move, we can lower the loads on the building. But if we get it wrong and we actually make the building stiffer than we intend to, all of a sudden we attract more load and our building fails. So we have to be very precise in making sure our building is not too stiff. So we want it stiff enough, but not too stiff. So you can see that the engineering of that becomes very difficult, especially considering that things like glass and cladding can add stiffness to a building that we might not have used in the strength design. So capacity design becomes a very, very rigorous process. In Toronto, we can just say, we're not doing capacity design, and we go about designing it for the maximum loads, which aren't that high because it's not a high seismic zone. But in high seismic zones, we have to work really hard at that design element. So the fees for seismic design might be quadruple, but it actually usually means that we have a great reduction in material, and the cost savings ends up being more than it would have been by just over-engineering it. In Toronto, it doesn't save any money because we don't get to take away much material, and we'd increase the engineering fees drastically. So now let's just look at a bunch of pictures, and then I have to sign off because it's my 4-year-old's first parent-teacher interview remotely. He got his report card yesterday. All right, we've seen all of these images before in the different lectures for the different materials, so I'm just going to go through them again quickly and show you what they look like. Lateral load resisting system, that's a diagonal tension compression brace. So here's a base detail of it. Diagonal tension compression braces, you can see that it gets quite muddy and difficult to connect there. These ones are quite slender relative to what they're doing, so my guess is they're tension only. So we allow it to buckle when it's under compression. So one of these is only working in each direction. So if I don't know what way this is going, if the wind is going in this direction, this brace is working. Or this brace is working. The one in tension is working. It's backwards, so it's throwing me off. If the wind is going in this direction here, this one is working, and this one buckles. If the wind is going in this direction, this one is in tension, and this one buckles. This might have been about capacity design, but I doubt it. Most likely, they needed a door right here, so they have an eccentric diagonal brace. Angles, definitely tension only, because these buckle so easy, they're tension only. Channels, probably also only tension only. You can see that there's some funny detailing here, because that ends up embedded in the concrete topping. Rods, tension only rods. Arena. This is a funny detail that engineers used to do all the time. You have to balance this to make sure you don't distort the circle in the middle, but it allows them to connect it easy. It became more of a type, a visual type. It works. You can see that they did bracing all the way around this tower. You can do unique diagonal bracing. K bracing, chevron bracing, V bracing. To me, it's very similar to truss names. I don't care what you call it as long as it works. So I certainly am not going to test you on what the names of that are, because who cares what the name is? We're usually looking at an image of it and we're doing the calculations to see what its capacity is. So who cares what the name is? Double chevron, you're going to meet other engineers who care a lot though. They really get worked up about it. V bracing. What we can do is super bracing. So for this floor right here, that's a brace, and that's a brace. For this floor right here, that's a brace, and that's a brace. But they've connected it so that for the building as a whole, this is the footprint of it. And if we don't think about what our connections look like, you can end up with some ridiculous detailing. We can do wood bracing. It's not very common, and you have to spend time thinking about what the steel connections look like, because it will be steel that connects it. This is most likely a capacity design joint, where they are limiting the load that can transfer through here, through this gusset. It looks really simple, but there's probably a ton of engineering involved in this. We can have bracing go all the way around a building. I always like to say you can take your lumps once or spread it out. So you can have one bay of super bracing, or you can have a filigree of lots of tiny bracing. So this would be take it in one big spot versus spreading it out around. We've seen this and we've talked about this before. And here we have a 3-pinned arch. So these two things are propped up against each other. So this is a piece of the frame, and it goes off camera, but both of these two things are propped up against each other, leaning against each other. Moment frames. Moment frames. You can see the members are a lot bigger. Pound for pound, there's way more steel in this than the equivalent braced frame would be, which means it's way more expensive. More steel means more cost, more steel means more tonnage, means more cost. And what we want to do is build the cheapest building we can within our constraints. So if there is no reason you can't have a brace here, put the frickin' brace in, because it's going to be cheaper. But if these are supposed to be big glass windows because it's a storefront, well then, yeah, your criteria says you can't have a braced frame, and then a moment frame might be a good option. But don't start at the moment frame. Moment frame. Wood shear walls. So wood shear walls, you can see here this diagram, we have to think about them. Contractors, probably 20 years ago, we didn't even design a lot of this for houses. The standard was just to put it up. And there's also been kind of load increases in the code in the past few years. There's a major switch in the code last year. I just have to check and see what time my student-teacher interview is, because I'm almost done and I don't want to have to end this. I have a few minutes still. They made a big change in the loading requirement a few years ago, and so projects that were being built or submitted for permit after June last year, or no, starting construction after June this year, either of those two things, for small or for narrow houses, it doubled the wind load. I have a project that's out right now, and the architect and the contractor are super mad at me. They think I'm just being a straight up jerk, and to the point that I actually reached out to other engineers and found if they were facing this same difficulty, and they are, that one night it switched, and you have to seriously increase what these designs are. So there is very specific nail spacing for these panels of wood. You need these anchors periodically so that the wood doesn't just shear off at the anchor. And then because the building's trying to tip over, you don't want this side to lift up. So we need these hold down anchors. So here are some details of some hold down anchors, different hold down anchors. Wood shear wall. You can have fabricated shear walls that come shipped to site. If you have a project where the contractor just is feeling slightly out of their element with the complexity of the shear wall, well, it can be a pre-ordered product from somebody like Simpson Strong Tie, where you give them the loads and the dimensions, and they will make the wood system fit in there, if they can. To make sure our building doesn't go out of square in plan, we need to make sure the floor works. So that would be our diaphragm. You can see the in-plane loads here. And there are very specific screw or nailing patterns for that. You can see that this is kind of like a mini moment connection. It puts bending in this post. So instead of just a pin connection, we've done something here. Remember I said that moment connections are often drawn as a solid triangle in plan. So if we had a column in plan and we had a beam, we would often draw in that solid triangle. Well, look, that's the triangle that we're talking about there. You might do a wood braced frame. Again, the wood bracing. I think I've told this story before in the wood building about the wood moment frames every 8 inches instead of 12 inches, and it's still deflected a lot, but you can see it's a narrow building. Concrete walls as our shear walls. A concrete core going in. My guess is this is a concrete building, but this could be a steel building, and it would still likely have the concrete core. Concrete portal frames, which is essentially a concrete moment frame. Not a common thing to do, but bridges are a different beast from most things. So what are your takeaway tips from today's lecture? Settlement is something we have to worry about. You need to be able to calculate the bearing capacity or the dimensions of a footing. You should know the bearing capacity of a slab on grade, 24 kPa. The depth required to prevent frost heave in southern Ontario, 4 feet below grade. And that we need a lateral load resisting system in every direction on every floor of every building, and you should know the typical lateral load resisting systems. If you know all that, you'll probably do pretty great on the soil and lateral load resisting system questions on the final exam. So again, it was fantastic having you all as students. Hopefully I'll see a bunch of you going forward if you complete your master's in architecture at U of T. If not, maybe you'll go on to some place like Waterloo where you'll meet my colleagues Corey and Andrea, who teach in that department. Or you'll be around at other universities. Maybe I'll see you in your careers out in the world. Hope you guys have a great exam, great holiday, and I wish you all the best. It's been fantastic, guys.